Hi, my name is Mayra Ishikawa. I am a PhD student at the University of Koblenz-Landau in Germany, and the title of my study is Comparison of the Application of Three Models of Distinct Dimensionalities for the Certification and Hydrodynamics of Passauna Reservoir. I'd like to start bringing some examples of applications of models. We have here the optimization of withdrawal for a drinking water reservoir, the study of sediment transport, algal blooms, and internal stages. Then, if you look at the keywords of these studies, we can have an idea of the related physical process. We have here thermal stratification, flow patterns, density currents, and so on. And now I would like to highlight the models that were used for these studies. We had from 1D to 2D and 3D models. Model dimensionalities, they bring pros and cons. 1D, they are fast, so they are good for long-term assessments, and they are easily connected to water quality. 2D, they still keep the lower computational costs and already bring more insights from lateral transport and hydrodynamics. While the 3D, they bring a lot of data with details, but with the cost of computational efforts. So the idea of this study was to apply three models of distinct dimensionalities for the same place and with the same boundary conditions. And then we interpret the results based on the simplifications of each model. We focus on water storage, temperature, flow velocity, and substance transport. The chosen models were GLM, the 1D vertical layer structure model with layer thickness that change dynamically. The volume is determined by a hypsograph curve, and the inflows they are inserted in a new layer of neutral buoyancy after an initial mixing that is estimated by the geometrical geometrical conditions of the inflows. C equal is the 2D V model, which means that it's laterally averaged, and it solves the Reynolds average Navier-Stokes equations with the hydrostatic assumption. So it is good for elongated narrow water bodies. And the 3D is Delphi 3D. It solves the same equations as C equal, but then in the three directions along the depth, the grids can be set as a sigma layer or Z layer. The sigma means that we have constant numbers of grids, but variable thickness, and Z layers is the opposite. And along the horizontal, we can have squared or curvilinear grids. In common for the two models, the 2D and 3D, we have that the equations are solved using infinite difference grid, and the grid is built based on the bathymetric method. And for the three models, we have the same drivers, hydrological and meteorological forces, and in and outflow conditions. For Delphi 3D, we also have the water level variations. Our study site is Passauna Reservoir. Passauna Reservoir is a drinking water reservoir located in South Brazil. It is a medium-sized reservoir. It has a maximum depth of 16 meters. Here at the entrance, there is a fire bay, which is an area of depth around 1 meter. So the waters get warmer here. This is the bridge that is over here, so there's a constriction. The main inflow is Passauna River, this one here. We have a water intake at this location, and here we have the dam with a spillway and a gate that has a continuous discharge. Here in front of the intake, we had a monitoring site, so all of the data is compared to measurements at this point, where we measured flow velocities with an ADCP and temperature profile with thermistor chain. The boundary conditions, some of the data were provided by our project partners, which is MUDAC VRM. The bathymetry and hypsograph curve came from a survey, and inflow conditions such as discharge and temperature, were modeled. And whenever we had measured temperatures, we used them. GLM had the implementation of 3 inflows. So the 2 main ones, Passaúna River and Ferraria River, and all the others, they were sum in volume and average in temperature. For Ishikawa and Delft, we implemented all tributaries. The meteorological conditions consisted in air temperature, wind speed, and direction only for the 2D and 3D model, shortwave radiation, relative humidity, precipitation, and cloud cover from the ERA 5 database. We observed the seasonal variation, but it was rated mild because the reservoir is located in a subtropical region. And variations on water level, they were small in the order of 1 meter along our period of interest. The model setup. We started in August 2017 and ended in February 2019. Period of interest starts on March 2018. When our measurement started, the first 7 months were the spin-up period. They all started with the same initial conditions in water and water level and in a mixed condition. And calibration was conducted with the aim to reduce the mean absolute error of temperature. GLM had the layer thickness fixed to a minimum of 10 centimeters and maximum of 50 centimeters in a time step of 1 hour. T-Qual had 2 segments with branches of approximately 150 meters width and 20 layers over depth, time step of 1 second. And F3D had a curvilinear grid of dimensions approximately 40 by 40 meters in Z layers, also 20 layers, and time step of 6 seconds. Jumping to results, here we have water level over time and the cumulative sum of the spillway volume over time. You can see that the variations are small. Actually calculating the error, they are basically the same, 10 centimeters. And the difference, they must come from the spillway or the evaporation because all the other things were the same. So for spillway, the 1D and 2D, they estimate the volume by empirical equations, while the 3D had the spillway as an open boundary. So that's why we have a decrease on the cumulative curve here. And the evaporations, they were significantly different, but in the same order. For temperatures, then we have here in colors the magnitude of the temperature over the depth here in the y-axis, and its time over in the x-axis. So we can see in this first panel the measurements where the reservoir was stratified at the beginning. In mid-April had its first mixing, and then it mixed and stratified several times as it is a polymictic reservoir, and then was stably stratified from September on. Looking at the 3 models, we can see that the 3 of them, they reproduce this seasonal variation, and actually calculating the errors, they are all in the same magnitude. But if we look at this error was calculated for all depths and for the total period. If you look at the temperatures for the errors for each layer, then we can see here, so is the error over depth and the correlation coefficient over depth, that the quality of the simulation is lost over depth. So the surface is the boundary that is better represented for temperatures. And we can see that here that Delft was better, although error was close, and also that GLM had lose the correlation over the depth. Then we also want to look at the stratification not only on temperatures, and we use Schmidt stability as a metric. and also to define mixed days with this threshold. So we have here Schmidt stability over time for measured and for the three models. And the gray background are the mixed days counted here. So we can see that GLN stratified more than the observations. When we look directly, the comparison of the Schmidt stability calculated from measurements and from the model, it is overestimating the Schmidt stability by a factor of 1.6, though the good correlation. Then C-qual had closer number of days from the measure, but it's not really guessing it right, although also a good correlation. And of 3D, it had the best correlation, but it has less mixed days than observed. We compared also the average temperatures at surface and bottom. We could see that GLM had larger temperatures at the surface and lower at the bottom, which explained the more stable stratification. And this is due to the simplification on space. So GLM does not represent the far bay that it is warming the inflowing water. So the bottom temperatures are in general lower and increases stability. C-qual had lower temperatures at surface and bottom, and delta had larger temperatures, the opposite from C-qual, which then explain the less number of mixed days because it's stratifying more. And since the reservoir is in a subtropical region, the stability is larger due to the larger temperatures observed there. And then flow velocities. Here we have in the first panel wind measured over time. We select a shorter period of day just to have a closer look on what was happening. And here the first panel, we have the measurements. The colors represent the longitudinal velocity. So we only compare the longitudinal to be fair with C-qual that only has this component. And negative values are going upstream and positive values are going downstream. So we can see that flow velocities are forced by wind, and then they have this behavior of opposing directions in the middle upper half and lower half of the water depth. Here, C-qual cannot reproduce this pattern. We can see that it is being forced also by wind, but not the same pattern. And Delft, it doesn't get right the intensities. They are lower than the observed, but we can see the same pattern. But interesting, calculating the errors, they were really close. And plotting the errors and correlation over that, as we did for temperatures, we can see that, yeah, they are close. And actually, the lowest error is at the bottom. So it's opposite from the temperature. The bottom boundary is a better represented boundary for flow velocities. And then looking at the correlation, we can see that C-qual is actually showing mainly noise because the correlation is around 0 and most of the time negative. And lastly, we added a conservative tracer at the Passaona River with concentration of 1 kilogram per cubic meter. And here we have the concentration of the tracer in colors at the intake region also. And the stars represent the maximum concentration of tracer within a day. With this, we would like to have an idea of the density currents. So here we consider a density current as an underflow when the maximum concentration is really at the bottom. So the flow is going along the bottom. Interflows were in middle depths. It overflows when the maximum concentration was really at the surface. Then looking in general, they all have the similar seasonal behavior, start from interflows, underflows, and then inter or overflows. GLM, it mainly had underflows and no overflows. This is also because because the far bay is not represented at the model. So the water doesn't get warmer and cold water flows along the bottom. C equal had mainly interflows and as well as Delft 3D, but C equal had less overflows. We can see that this maximum concentration was mainly trapped in a layer. So it indicates that it was entering under the surface mix layer, and while Delft it was the opposite, and that's why this maximum concentration was scattered over the surface. So as conclusions, before I would like to mention that computational costs must be considered. This is usually a bottleneck when choosing a model. The 1D 1 in seconds, 2D in minutes, and 3D in 85 hours. Also, if you invest more time in calibration, this could bring you better results. But anyways, all the models had the capacity of represent the seasonal temperature stratification. The simplifications of the 1D model overestimate the stratification. The field of fluid losses could only be represented by the 3D model. And a common limitation was the surface mix layer depth. This can be problematic later for water quality models because overflows, this influence on the density current, and overflows are delivering nutrients at the aquatic zone, while the others are trapping nutrients in deeper layers. And here there is a small table of applications. So 1D models are capable of give good results in studies of mass balance and water level. This is an operation that depend on stratification. The 2D can also add a substance transport and density currents analysis, and the 3D brings all of that plus the flow velocities. Yeah, that's it, and thank you for your attention.